All right, welcome to the last, should hopefully be the last lecture in the last chapter of this course, where we're going to use everything we've learned to solve some specific Diophantine equations, or Diophantine equations of a specific form. And we're going to do this by using our machinery of class groups and so on. But before that, let me just give you an easy example where we don't need to use any of the machinery, but it'll guide us to the ideas of what we want to use. And it's the following. So say, let's find, so what's a Diophantine equation? You have some polynomial, maybe one or two variables, three variables, and you want to figure out what all of the solutions are with the variables only allowed to be integers. That's what Diophantine equation is. So let's find all integral solutions, or integer solutions, to the following: x cubed equals y squared plus 2. So say you were given this and say, find me all the integer solutions to this thing. And we can do this without most of the machinery we've developed. Let's somehow work through this. So for starters, let's factor this. Let's factor the right hand side of this, the right hand side, in z adjoin the square root of minus 2. Why this? Well, because I have an x squared minus 2, so I can write this as x cubed equals y minus the square root of minus 2 times y plus the square root of minus 2. Great. I'm going to factor this in this, which, notice that is a unique factorization domain. So I'm going to use this factorization domain. So that this means I can do factorize things into irreducible numbers, into reducible elements, uniquely up to units and so on. So let's try and use this to solve this equation. So I factor this as follows. So I factor this as x cubed is y minus root 2 minus 2. And now I want to say that these two factors are distinct, and in fact that they're co-prime. So I claim that y minus square root minus 2 and y plus the square root of minus 2 are co-prime in this ring, z adjoin the square root of minus 2. Let me prove this claim. How do we do this? Well, if you had any element dividing this and this, it would have to divide their sum and their difference. So in particular, if they had a common factor, so if there was something that divided both of them, it would divide their difference. So it would divide this minus this, for example. So it would be a factor, i.e. it would divide what is it? So difference 2 minus the square root of minus 2. Great. I think maybe in the first lecture, and I gave you some motivation, the first problem class where I went through some motivation, I maybe mentioned a similar example to this. But let's do this again. So it would divide their difference of these two elements, of these two things, which is this thing. Meaning that x would be even, right? If 2 plus the square root of minus 2 was a factor of these two things, then so it divides this right hand side, so it would have to divide this left hand side. There's a 2 here, so this x is going to have to be it would have to divide this thing, and any square or cube power this has a 2 in it, so x would have to be even. So x cubed is divisible by 8. No, would be divisible by 8. by 8. So this thing would be divisible by 8. But now the right hand side can't be divisible by 8 because y squared plus 2 is never 0 mod 8. But y squared plus 2 is never 0 mod 8. Just work that out. Well, it's never even a multiple of 4. So so this can happen. Can't happen. So these elements are coprime. Great, so I have a coprime factorization. So if I have an element which is a cube, which is a product of two things, each of the two things has to be a cube up to some unit. So up to a unit, we have following, each of these things has to be a cube. So for example, let's do the other one, plus 1. For example, this element has to be the cube of something else. So it has to be plus or minus some beta cubed for beta some other element in z square root minus 2. Right, in a UFD, this is what has to happen. Because minus 1 is a cube, I can absorb this minus 1 into my beta. So I might as well just assume it's some element like this. So if I let beta be some random element, so if I let it be u plus v times the square root of minus 2, what do we get if I just plug this in? We get y plus the square root of minus 2 equals u plus v the square root of minus 2 cubed, which I'll expand out, and you get u cubed plus 3u squared v square root of minus 2 plus 3u v, so we 6 minus 6 uv squared minus 2v cubed square root of minus 2. So we have some equality like this, and now we just compare coefficients. So comparing coefficients of the square root of minus 2 and coefficients of on each side. What do we get? So equating coefficients. What do we get? We get y has to be u cubed minus 6u v squared, and 1 would have to be 3u squared v minus 2v cubed. This is the coefficient. The coefficient of square root of minus 2 is 1 here. If you put this together, the coefficient of square root of minus 2 is 3u squared minus 2v cubed. So you end up with these two equations. What does this imply? This implies, if you look at either one of them, I guess. If you look at this one, whatever v is, v divides the right hand side. So you notice that beta is some element of here. So here, let me just write u and v are elements of z. So v divides this side, so it has to divide the left. So v has to divide 1. So what does this implies v divides 1, i.e. v is plus or minus 1. So if I plug this in, you get y equals u cubed minus 6 u, and 1 equals v times 3u squared minus 2. I don't know, v is plus or minus 1. I'm not sure exactly which of the two it is. So you get something like this, which again, if you look at this equation, now this implies implies you have u has to be plus or minus 1, and v has to be 1 out of the two options. So I know what my options for u and v are. That tells me what the options for beta are, and I know what I know that y is something like this, and I have all the options for my solution y. And then once I have that, then I can substitute back to get all my solutions of x, because I know that x cubed is y squared plus 2. So I know that this is that. So y is plus or minus 5, which implies x is 3, if you work this out. So all solutions are either 3 and 5 or 3 and minus 5. So this is a very elementary way of solving, I say elementary, this is a very, what one would consider a low, or something with low on MCAT tools to solve the, fine. An elementary way of solving this equation, where all the thing that we really use is the fact that this thing is a UFD. In general, if this wasn't a 2, but it was some other element, so the type of equation that we're going to solve will look like this, but this 2 will be changing to something else, or sometimes you can get like a y squared plus y plus something else term. Well, sometimes they essentially look like x cubed equals some quadratic in y. This is, if you don't elliptic curves, of course, this is some elliptic curve. If we had something that wasn't 2, then this thing might not be a UFD, and then our argument wouldn't work, because we can't factor things uniquely if you're not in a UFD. The trick is, well, we don't have all of this theory about ideals, and we don't have to factor things uniquely into elements. We can factor things uniquely into prime ideals, and then we can use the same basically strategy that we've done here to find what all the solutions are, but working with ideals instead. So we want to see what to do if we are not in a UFD. So here, let me give you two lemmas that we've proven already in the course in one of the problem sheets, which will be quite useful. So lemma 5.0.1 says, let K be a number field. I'm mainly reminding you of these lemmas. You'll know these already, I guess, hopefully. If I have two elements in my ring of integers, if as ideals that they generate are the same, then they differ by a unit. So you can write alpha as u times beta for u some element of OK cross, and so hopefully that lemma is almost obvious for you. And lemma 5.02 is about factorizations in ideals of a cube. So here I remember I noticed that I said at one point, because the product of these two things is a cube, and these things are co-prime, and they have to be a cube. Well, here's the analogous statement but for the ideals, and this works for Dedekind domains. So let R be a Dedekind domain. And let's take A, B, and C ideals. Such that A times B equals C cubed. And let's assume that A and B are co-prime, i.e., remember what this means in this case. Well, we have either GCDs, or in this case, it also just means that if you sum them, they give you 1. Then there exists ideals. Well, I'm not sure how I'm going to write these. E and D, I guess, such that A is E cubed, B is D cubed, and E times D is my ideal C. Great. So this was done in the problem sheet, but this was also done in the problem sheet. So if you have a product of two things is a cube, and the things are co-prime, then each of the things has to be a cube. Essentially, this is just for ideals. So using these two things, we can generalize the previous strategy for other types of Diophantine equations. So here's an example of how we can use this. So let's find all integral solutions to x cubed equals y squared plus 74. And in this case, I'm going to give you a fun assumption. I'm going to assuming that the class group of the relevant field has size, well, the class number, that if k is q square root of minus 74, so I'm giving you this so that we don't have to compute it. So I'm telling you the class number is 10. One could, the assumption is just so that you don't have to, so that we don't spend our time calculating the class number. But in the exercise in the problem sheet, you'll be like given, you'll see, you're given a field, you have to calculate first what the class group is, and then using that you'll solve some Diophantine equation. But let's assume that we know what the class group is 10. And I'm going to tell you that once we know these two things, this thing, then we can figure out what all the solutions to this Diophantine equation is. So again, the trick is to factor this expression. In this case, it's going to be OK, which we know is z square root minus 74. But first, the following. So here's the, let's assume that we had x and y as solution to this. We can already rule out, just some elementary analysis will rule out some possibilities for what x and y can be. So first note the following. Assume x and y and z are solutions. Note that first of all, y can't be even, because if y was even, right, then this right hand side would be even, which means this left hand side has to be even. So if 2 divides x cubed and x is an integer, that means 8 divides this. Then 8 would have to divide the right hand side, but 8 can't divide the right hand side because 74 isn't divisible by 4 essentially. So y can't be even, since this would make x even, but then if you consider like x cubed minus y squared, well, then this would have to be congruent to 0 mod 4. But so I'm just taking the y to the other side. I'm saying that this is the difference of x cubed and y squared is divisible by 4, but 74 isn't divisible by 4. 4 doesn't divide 74, so x and y must be odd. So this is just some simple observations just in the integers of what happens with these x and y. I'm not working in this field at the moment. I'm just working some simple observations that y can't be even. So x and y must be odd, and also they have to be almost a similar kind of proof. Well, a similar kind of statement is that they actually have to be co-prime. X and y have to be co-prime. Similarly, x and y must be co-prime. I guess I could have just proven this from the start, but let me just work our way in. Similarly, x and y are co-prime, since obviously if p divides divides both, then p squared would have to divide their difference, so p squared would have to divide 74, which is x cubed minus y squared, but 74 is square free. So, so this can happen. This can't happen. Okay, so we haven't do any fancy stuff. X and y must be co-prime numbers, and neither of them can be even. Great. So now let's do the same sort of thing that we did before and factor this expression in, as I said before, in here. So I've told you that the class number is 10 of this field. So this ring of the class number of this thing is 10. So this ring of integers isn't a UFD. It's very far from being a UFD. This is a very big class number. Well, big. The class numbers can be as big as you want, but this is not 1, so this isn't a UFD. So we have to actually use something here. So let's factoring in OK. We get, what do we get? We get x cubed is y minus the square root of minus 74 times y plus the square root of minus 74, like this. And we want to consider this because factorization isn't unique. So since OK is not a UFD, we need to go further. And consider this as a factorization, well, as ideals. So as ideals, i.e., you look at the ideal generated by x cubed has to be, I'm going to use the same notation, but now I'm talking about ideals. The ideal generated by y minus the square root of minus 74 and y plus the square root of minus 74 as ideals. Right. So if I have some equality like this, doesn't matter if this is unique or not, but when I take it this as ideals, this ideal generated by x cubed has to be these two ideals. Now what I want to say is, because I have a cube here, I want these two things to be, I want to see if these two elements have to be cubed. So what I want to check is that these two ideals are co-prime. I want to check that the ideal generated by this and the ideal generated by this are co-prime ideals. So this is so that I can apply my lemma 5.0.2, because I have two ideals, a times b, which is something cubed. If they were co-prime, then I can write each of them as, as an e and a d. Each of them would have to be a cube, which is somehow what we did in the first. This is following the recipe that we did for the first case. So are the ideals on the right hand side co-prime? That's the question. Let's see what would happen if it wasn't. So if some prime ideal p a prime ideal divided both of them, we would have, what would we have? We'd have y minus the square root of minus 74 to be congruent to 0 mod p, and y plus the square root of minus 74 would also have to be 0 mod p, mod my ideal p, my frac p. So p divides both of these two things. So as before, it'll divide their sum or their difference. So p divides, in this case would be 2y, which is the sum of these things, and p would also divide, okay, well, so this is, well, we just need to consider their sum. So p divides their sum, i.e. the prime ideal p divides also sum of these two things, which is 2y, generated by 2y. If you look at the other side of this of our equation that we have over here. This means that, or just on this side, so this means P would have to divide the ideal generated by X. We know that X is odd, so P can't divide 2. This can't. X is an odd number, so the ideal that generates, I'm saying, can't be divisible by any ideal that divides number 2. Well, you can see in the notes why this is the case, but think about why this is the case before you look up in the notes why this is true. So what do we have? We have P divides 2y, but it doesn't divide 2. So P divides y, and P divides the ideal generated by X, but X and Y are co-prime, so are their ideals. So are the ideals generated by X and Y. Therefore, you can't have any. They're co-prime, so they can't have any ideal that generates both of them. Therefore, therefore we can't have P dividing both of them. So it's a contradiction. So clearly, there can't be a prime ideal dividing both this and this. Okay, so these two ideals are co-prime. So I am now in the statement of my lemma. I have two ideals which are co-prime, and it multiplies with an ideal cubed. So using lemma 5.0.2, what do we have? We must have this ideal. Each of them has to be a cube of some other ideal. So this minus square root of minus 74 has to be some ideal cubed. Similarly, y plus the square root of minus 74 has to be some ideal b cubed with a times b, the ideal generated by x. What does this mean? So let's think about what this means for these ideals as elements of the class group. This means that in the class group, what do we have? The ideal generated by A, by frac A, cubed, which is this thing, has to be 1. Similarly for the ideal generated by B cubed. So this, if A wasn't trivial in the class group, then this class group would have an element of order 3. But we know that the class group has order 10. And by Lagrange, the order of an element divides the order of a group. So the class group has order 10. So we can't have any elements of order 3 in my class group. So we know that A cubed is 1, but in fact A has to be the class of 1, because we can't have any non-trivial elements of order 3. In the class group we have this, but the class number is 10, so we can't have any ideals, can't have any elements of order 3. So the class of A, so when I have that A cubed equals 1, that means that the order of A is either 1 or 3, right? So I'm saying it can't be 3, so it has to be 1. So this has to be this, and the same for B. So each of these ideals has to be the class 1, so each of these ideals has to be principal. So A has to be principal. Therefore, what do we have? So we have y minus, say, the square root of minus 74. This has to be some ideal, say A plus B square root of minus 74 cubed. It has to be the cube of some principal ideal. Now, I have some equality of ideals, some equality of principal ideals. So now I want to use my first lemma. If I have two elements and the ideals are the same and they differ up to a unit, and in these quadratic fields, I know what all the units are by one of the exercises in the problem sheets. So by lemma, what is it, 5.01, and something that tells me what all the units are, in quadratic fields, exercise 3.15 of the notes, we see that up to a unit, so in this case units are plus or minus 1, we can expand these two things out and compare coefficients. So what do we have? Well, first of all, we have this is I can expand this out, so I get a cubed plus 3a squared b square root of minus 74 times minus 3 times 74 times b squared a minus b cubed 74 times square root of minus 74. So now we're basically back to somehow what we were doing in the first example. I compare coefficients and then I can somehow figure out what my my solutions are. So equating each side, we get that y has to be a cubed minus 3b squared a times 74. Not sure why I wrote it down like why I didn't multiply it. Let's do 3 times 74 times b squared times a. And on the other side I have 3a squared b minus b cubed 74 equals 1 by comparing the coefficients of the square root of minus 74. Notice that a and b are integers. Here, a and b are in z. So b divides this side, so b has to divide 1 again. So b has to be plus or minus 1. So the second equation implies b divides, in this case I guess it's, sorry, I got made a mistake. This is minus 1, so b divides minus 1, so b is plus or minus 1. This gives, if you substitute in, this gives a is plus or minus 5 on this side, the possibilities for a. So now we know what a and b are, so we substitute this in and we figure out, on this side we figure out what y is. So y is either plus or minus 9, 8, 5, and you'll figure out that x in this case has to be 99. So the only solutions are are 99 comma plus or minus 9, 8, 5 for x and y, and we're done. Notice that if you wanted to do this, if you're trying to do this by hand, you'd have a really hard time to find these solutions. These aren't very easy, but we can do this with number theory, with our course stuff, and you can do this for other stuff. You'll see some more examples of this. So there's other examples in the notes about another example, but it's basically the same as this one, but in that case you end up proving that there's no solutions. But I'll let you to go through this. But yes, this is the end. We've computed class groups. We've now computed computed solutions to specific Diophantine equations. In particular, in this case, are some special curves. And yeah, that's it. That's the end of the course, chapter 6. You don't really have enough time to finish properly, so I'll just leave it as a non-examinable read yourself sort of thing. And yeah, this is the end. All right.